Have you ever pondered why the solid ground beneath us sometimes trembles and shakes? The very thought can be quite unsettling, can't it? This is the mysterious world of earthquakes, a phenomenon that simultaneously incites our curiosity and sends chills down our spines. Its unpredictability makes it all the more fascinating and terrifying. But what if we told you there's a science behind these earth-shattering events? To comprehend this, we need to venture deep beneath the surface to the heart of our planet. Our Earth, a seemingly solid sphere, actually consists of several layers. Let's imagine peeling an onion layer by layer. At the very exterior we have the crust, a thin shell on which we all live. This crust isn't a single piece, but rather a jigsaw puzzle of massive slabs known as tectonic plates. Beneath the crust we find the mantle, a thick layer of hot, semi-solid rock. Think of it as the Earth's insulation, keeping the core's heat from reaching us. Now let's burrow even deeper to the core, our planet's very heart. It's divided into two parts, the outer core, a sea of molten metal, and the inner core, a solid ball of superhot iron and nickel. Each of these layers plays a crucial role in the Earth's function, but the crust, with its tectonic plates, holds particular interest for us. These tectonic plates are the key players in the drama of earthquakes. Imagine these tectonic plates as colossal rafts, floating on the semi-fluid mantle beneath them. Each of these rafts or plates is a massive chunk of the Earth's lithosphere, which includes the crust and the uppermost mantle. They're not static, sitting in one place. Oh no, these plates are constantly on the move. This movement is driven by the intense heat energy radiating from the Earth's core and the semi-fluid mantle. Picture a pot of soup heating on a stove. As the soup heats up, it starts to churn and circulate. This is convection. Similarly, the Earth's internal heat causes a convection current in the mantle, driving the tectonic plates on their continuous journey. Now, these plates don't just glide smoothly past each other, they're more like reluctant dance partners, each trying to lead. Some plates move away from each other, creating a gap that magma rises to fill, forming new crust. This is called a divergent boundary. At other times, plates collide head-on, with one being forced beneath the other in a process known as subduction. This is a convergent boundary. And then there are transform boundaries, where plates slide past each other, neither creating new crust nor destroying old. Each of these interactions can cause intense stress and strain. When this stress becomes too much, the Earth releases it in the form of seismic waves, what we know as earthquakes. The real action begins when these plates try to move past each other. When tectonic plates attempt to slide past each other, they often get stuck due to the rough and jagged nature of their surfaces. Now let's delve a little deeper and understand how this results in an earthquake. Imagine two enormous rocky slabs locked in a titanic struggle. The plates, each covering vast areas of the Earth's surface, are constantly in motion, but when they try to glide past each other, the jagged edges of their surfaces catch, causing them to stick. This is where the drama begins. The stuck plates don't just give up and stop moving, far from it. The rest of the plate continues to move, causing an immense amount of stress to build up at the point where they're stuck. This stress is like a simmering pressure cooker, building up over time. It's a silent, invisible force, yet it's powerful enough to change the shape of the landscape, bending and warping the rock at the fault line. But rock, despite its solid appearance, can only take so much. At some point, the stress becomes too much. The rock fractures, and the plates suddenly slip, releasing all that pent-up energy. This is the moment we refer to as the birth of an earthquake. This energy doesn't stay put, though. Like ripples spreading out from a stone thrown into a pond, the energy radiates out in all directions in the form of seismic waves. These waves, invisible to the naked eye but detectable by seismographs, travel through the Earth, shaking and jostling everything in their path. The point directly above where the earthquake originates, on the Earth's surface, is called the epicenter. These seismic waves are what we feel as the shaking and trembling during an earthquake. They can be incredibly destructive, toppling buildings, triggering landslides, and even causing tsunamis when they occur under the ocean. And thus, in an explosive release of pent-up energy, an earthquake is born. It's a powerful reminder of the dynamic, ever-changing nature of our planet, a testament to the immense forces at work beneath our feet. But how do we know how powerful an earthquake is? Well, that's where the Richter scale comes into play. Developed in the early 20th century by Charles F. Richter, this scale gives us a standardized way to compare the energy released by earthquakes. Here's the interesting part. The Richter scale is logarithmic. What does that mean? Well, each whole number increase on the scale represents a tenfold increase in measured amplitude. So, an earthquake measuring 5 on the Richter scale is 10 times more powerful than one measuring 4. It's an exponential increase, not a linear one, which is why a seemingly small jump in the numbers can mean a substantial increase in earthquake severity. This scale, along with other sophisticated monitoring tools, helps scientists not only understand the power of earthquakes, but also predict future seismic events. Understanding earthquakes is not just fascinating, it's crucial for our safety and survival on this dynamic planet.